let's do some Hardy-Weinberg practice problems. So the very first question is pretty easy because they give you one of the frequencies of the alleles. So here they told you that Q equals 0.8. Remember, Q is the frequency of the recessive allele, in this case little a, in our population. So I can fill in that Q equals 0.8. Knowing that P plus Q equals 1, I can now figure out P. P is simply 1 minus 0.8, because P plus Q has to equal 1, so P in this case is going to equal 0.2. Knowing those, I can simply use the other side of the equation to figure out the rest. So P squared is simply going to be 0.2 squared, which gives me 0.04. That's how many individuals in this population are homozygous dominant, big A, 4% of them. Q squared, I simply take 0.8 squared, and that gives me 0.64. That tells me that in this population, 64% of the individuals are going to look like the recessive. 2PQ, I take 2 times, not this one, that's P squared, we have to go over here, 2 times P, which is 0.2, times Q, which is 0.8. So 2 times 0.2 times 0.8 gives me 0.32. Double check my answers by adding these three up. 4 plus 64 plus 32, it equals 1. Because P squared plus Q squared plus 2PQ also equals 1 according to Hardy-Weinberg. Alright, the next type is slightly harder because we're talking about the number of individuals. Anytime it talks about the population, the number of people, or the number of rabbits, or the number of moths that have a certain trait, we're going to use this side of the equation. And it says the number who are homozygous recessive. That's right here. Little a, that's homozygous recessive. So whatever number they tell us, that's going to be my Q squared. 9 out of 100. If you enter that in your calculator, or if you just know it off the top of your head, 9 out of 100 is 0.09. That's Q squared. Now remember, my equation for this side is P squared plus Q squared plus 2PQ equals 1. I can't simply subtract 0.09 from 1 to figure out the rest. There's too much complicated math there. But I can use this side. This is a much simpler equation. P plus Q equals 1. So all I have to do is go from Q squared to Q. What is the opposite of Q squared? The square root. So if I take the square root of 0.09 to go from Q squared to Q, here's my number for Q squared, take the square root of that, that gives me 0.3. Now I can use my nice simple equation, P plus Q equals 1, to figure out what P is. P would be 1 minus 0.3, and that gives me 0.7. So this tells me how often we see a little a or a big A in our population. Let's go back over here and figure out how many people actually look that way. So for P squared, we take that number, 0.7 squared, and that gives us 0.49. So in this population, 0.49, or 49% of the people, are big A, homozygous dominant for this trait. 2PQ, we're going to take 2. Once again, we use these numbers, not these. 2 times 0.7 times 0.3, and that gives us 0.42. So in this population, 42% are heterozygous, 9% have the recessive trait, 49% are homozygous dominant. So if you were looking for how many people look like the dominant trait, sorry about that. Okay, so if we add up, these guys have a big A, and these guys have a big A, that'll tell us how many total people look like the dominant. So, for example, we could do brown hair. So these people have the brown hair gene, these people have the brown hair gene, so we could add those up. 42 plus 49 is going to give us 91% of our population that looks dominant. Okay, let's try one more. This is probably the hardest Hardy-Weinberg equilibrium problem you would ever be given. And in fact, it's probably beyond what I would ask you on the test, but just in case, I will show you how to do one of these. So the key here is that it says that the dominant trait is 64 out of 100. And we're looking for how many are homozygous recessive. So knowing that 64 out of 100 are dominant, that includes these guys and these guys. There's no easy way to break that apart. I don't know how many are heterozygous or homozygous dominant for this trait. So the one that I do know and I can figure out very easily is what's left over. Q squared. I should start there. So if 64 out of 100 are the dominant, here, what's left over? I can take 100 minus 64. That gives me 36. So my Q squared now is going to be that remaining 36 out of 100, which is 0.36. Remember, because I didn't know how that 64 was balanced between those two. Knowing that this is 0.36, I can go over here to this side. I know that Q is going to be the square root of that, because that's the opposite of Q squared. So, square root of 0.36 is 0.6. I can use my simple equation, P plus Q equals 1, to figure out what P would be. It's going to be 1 minus 0.6, which gives me 0.4. Now I've got everything I need to fill out the rest of the box. So P squared is simply going to be my 0.4 squared. Got my 0.4 from here. 2PQ, so that equals 0.16, and 2PQ is going to be 2 times 0.4 times 0.6, and that gives me 0.48. So remember that original 64 out of 100? There was no way of knowing that it would be 16 here and 48 here unless I first solved the Q squared. Those are my answers. Hope this helps you guys. If not, send me a text message or an email and I'll get back to you with whatever help I can.